All right. Well, good morning, afternoon, evening, wherever you are. To everyone, thanks for joining this talk. I'm going to talk about confidential computing and containers, and I want to give a heads up first. This is very much work in progress. This is something that's being currently discussed, and it's been discussed for not such a long time, a few weeks only, in the Kata containers community. So I'm going to present this. I'm going to explain where we are, what kind of architecture we're looking at, and yeah, keep in mind that this is currently being discussed. So whatever I'm presenting here might change in the few weeks and days. So confidential computing containers. Yeah, confidential computing may sound to many of us as one of those cloud buzzwords, I would say. But it's actually it's trying to build a very interesting set of use cases and essentially trying to bring a new kind of threat model for the cloud. And if we look at the current one, the existing typical threat model, where basically as a guest you have to put everything that the infrastructure owner brings into your TCP. You need to trust the hypervisor, you need to trust the hardware, you need to trust the firmware, the host firmware, the kernel, everything. And from a very high level point of view, the confidential computing goal is to remove a lot of this stack out of the guest TCP. So with a correct implementation of confidential computing, one would be able to not trust, I would say, any of those green component there on the host. So you wouldn't have to trust the host kernel, the host OS, the hypervisor is out of the TCP. And essentially, with confidential computing, we're trying to completely remove the host stack from the guest TCP. And the interesting point, and that can be summarized in one sentence, is that with confidential computing, you no longer have to trust the infrastructure owner. So you don't have to trust your CSP, you don't have to trust your private cloud owner or operator. Just have to trust yourself. And as a tenant, you are the only one that can see and modify your data. That's the goal of confidential computing. So it's a very interesting goal. I think there's a lot of use cases for this. A lot of people are interested in this. It's pretty early in the life of confidential computing to see a lot of implementation out there, but it is very interesting. And essentially, confidential computing is the goal of confidential computing, and how we build the threat model is achieved through mostly two things: data protection and attestation. And data protection is it's a very vague description of things, but essentially, when as a tenant, your data can be in mostly three different states. It can be in transit, and that's a nice word for saying that it's going through some networking pipes. And we already know how to protect that. There's TLS, a bunch of VPNs. Well, there's many different ways where you can protect your data while it's in the somewhere in the network. Your data can be addressed. It can be stored somewhere. And again, this is something I believe we know how to protect. We have disk encryption. There's a lot of discussion also currently happening about encryption of container image layers. So we kind of know how to do this. The last thing is data in use. What happens to your data while it's being computed, while it's being in memory or in somewhere in your CPU caches and registers? Well, we don't really have a story for this. And the confidential computing goal is really to fill that gap together with attestation and make in-use data protected. And by, again, the in-use data is really when your data is being processed by a processor somewhere, and typically it's going to be loaded in memory and in your CPU caches and register. And what many of the confidential computing implementation, and I will talk about it a little bit more later, but they're hardware implementation mostly, well, not mostly, they're all hardware implementations. But what they provide are memory and CPU state confidentiality and integrity. So they that's the feature they provide for protecting your in-use data. Protecting data for reaching the threat model that the confidential computing is trying to build is not enough. You can protect your data, but if your data is not the right one from the very beginning, it's kind of a nice little backdoor that you have there and that people could take advantage of. So as a tenant, you not only want your data to be protected from your host, but you also want to be able to attest two things. The first one is that the platform, the hardware platform that you're running on is the right one. You want to be able to attest that it actually is providing the right hardware features for doing confidential computing. And you want to be able to attest your own software stack. You want to make sure that whatever you're running and building is exactly what you asked your workload to be running. So when we combine those two features, in-use data protection together with attestation, we can reach this and we can build this new threat model. But obviously, this is all done by some piece of hardware. We need hardware assistance to build confidential computing. And there are a few technologies out there that are trying to implement this or implementing this from different vendors. AMD has SEV in various forms, IBM has PEF and secure execution, and Intel with TDX and to some extent SGX is also trying to provide the right hardware features to build the confidential computing threat model. One very important point about all of this is that all those technologies, all those hardware features, they are designed and architectures are as hardware virtualization extensions. What I mean by this is that they're designed with virtual machine in mind, and they assume that confidential computing workloads will run in virtual machines. So if you want to build a software stack that leverages confidential those hardware features and build this new threat model, you're only going to be able to access that through the hypervisor, through KVM or Hyper-V, but through the hypervisor API. So a confidential computing workload runs in a VM, and this is a very important thing to keep in mind. Another thing as a reminder, runC does not talk to KVM, and runC will launch workloads that are not running in the virtual machine. So what if we want to build and run confidential computing containers? Well, our container workload must run inside a virtual machine if we want to be able to use those hardware features. And we need basically if we look at the very high level architecture, we need this kind of architecture. We need to have container runtimes like containerd and CRI-O talking to runtime implementations that would basically start some sort of virtual machines and run the pods, Kubernetes pod, or even directly containers inside those virtual machines. And while there are a few implementations that do that already, to name a few, Kata containers is one of them. Firecracker as a whole also does that. gvisor is also providing this kind of implementation, although not exactly that architecture, I think. And what we're going to talk about here is Kata containers. Kata containers is a very natural fit for this architecture. It talks to the hypervisor APIs through different sort of VMMs, QEMU, Acorn, Cloud Hypervisor, and we believe it's a very natural fit to implement confidential computing for containers. There are a bunch of gaps for things, something like Kata containers to implement confidential computing. As I said, we need to provide data protection to the guest workload, and we need to provide attestation. When combining those two, you can build this new thread model that people want to use. And when you look at data protection, we need to be able to enable memory encryption and CPU state protection, and that goes through a new set of VMM APIs. The QEMU, some QEMU APIs, protecting memory APIs from QEMU, for example. Cloud Hypervisor is also implementing this. So we need to have Kata containers understand and cover those new APIs. We need to be able to tell Kata containers that we want to run a confidential computing container. So that's going to come through some new additional configuration knobs for Kata containers as a runtime. And again, this is something that's being discussed in a specific issue that I'm going to link to at the end of this presentation. So we Kata containers will come with a set of probably a small set of new configuration knobs to kind of let the Kata shim know that it needs to enable memory encryption, enable CPU state protection and integrity. And well, if you go up in the stack, we also need to provide new runtime classes for this to be triggered. So we need to have Kubernetes being aware of part of this at least. Enabling memory encryption and CPU state protection, integrity is one thing, but there's another thing that I didn't yet talk about is how we're going to protect the container images from the host. Currently, how Kata container works is that Containerd or CRI-O will mount a container image on the host and basically paravirtualize those mount points into the virtual machine that Kata container is going to build for the container workload itself. Containerd and CRI-O mounting a container image on the host is, well, completely breaking the thread model that we talked about when we don't want to trust anything from the host, from any pieces of the software stack. So there's a big there's a pretty heavy lift that we need to do for this, which is basically offloading the image services away from Containerd and CRI-O and basically moving it into the virtual machine that's going to run the container workload itself. And the image downloading, mounting, pulling, and storing is going to happen from the virtual machine itself. And last but not least, the container images will be decrypted inside the guest and encrypted back inside the guest as well before being stored somewhere in a host-driven endpoint. Could be a local storage, could be a networking endpoint. It doesn't really matter, but essentially what comes out of the virtual machine with confidential computing containers must be encrypted, and what comes in must be encrypted as well. And decryption and encryption happens inside the virtual machine. To be able to decrypt container images, we need the attestation process to be done and completed in order to provision our workload with some keys and use those keys to actually decrypt the container images that we will pull from inside the virtual machine again.
Hey, Samuel.
Was there some?
I just have a couple of questions, if you don't mind.
Sure.
You mentioned Kata containers and Firecracker, but what about libkrun? Could that allow also the confidential computing?
Sergio is on. I think he's on a call. I think it would be. I don't think it would be well. I'm gonna quickly describe the architecture that we want to go through, and there's some fairly heavy guest enlightenment that we need to put in place for doing confidential computing. Attestation is going to happen in the guests. Container image offloading is also going to happen in the guest. So I think there would be some need for having some sort of agent inside the guest. And I think, and Sergio, please correct me if I'm wrong, but I don't think there is such thing right now with libkrun. So I'm not. I mean, I don't see why it wouldn't be possible. But I think it needs some more.
I see.
The same applies to Kata containers. Yes.
And then there's discussion going on about why would Kubernetes need to know. I can't remember what that is, but why couldn't there be something in the image that tells Kata to run in confidential mode?
Well, you could do that as well, but you need to. Ideally, your container image should be unmodified for running confidential computing or not. So, I think it's very convenient to be able to use the same exact container image to run confidential computing or not. And one reason for this is because, and I'm highlighting this in the issue where this is currently being discussed, but there's quite a few hardware limitations when it comes to scaling containers on the node. So you may be facing a situation where you don't have enough resources for running all your workloads through confidential computing. So you would want to be flexible there and not have like two sets of container images, one for confidential computing and one for not doing this. So I think what we're currently discussing in the issue leads to some sort of maybe not Kubernetes awareness of confidential computing, but being able to pass specific pod annotations for basically tuning the kind of confidential computing that you want to do. So we're already seeing some hardware technology implementation having some very specific configuration that they would need. And I think this would be this is not a runtime specific configuration. It's really a workload specific configuration. So we would need to, from a Kubernetes perspective, we need to be using the right runtime class with the right pod annotation. I think this is what's gonna happen in the end. Sure. Where was that? Oh yeah. Okay. Attestation. And here as well, I'm going to talk about this attestation as something that happens after the guest is launched. After the workload is running and the Kata agent is up and running, and basically the current architecture proposal is to make attestation happen from the Kata agent, but some people are already highlighting the fact that for some of those technologies, like AMD, the previous version of SEV, they're expecting attestation to happen before the guest is actually starting. So this may be something that we need to adapt to support previous versions of confidential computing implementation. But what I'm describing here is assuming that we can do user space attestation, and this attestation will be implemented from the Kata agent. So the Kata agent, everything on the guest up to the Kata agent would be measured and being able to be attested, and the Kata agent itself would do the attestation process. And once the tenant is able to attest that the guest stack and the container virtual machine stack is exactly the one that is expected, it could provision the container workload with keys to be able to decrypt the container image that get pulled and then decrypt. But the key provisioning in that architecture comes after the attestation. Okay, so I have 5 minutes left. Quickly here, this is the current high-level view of the current Kata container stack, where basically Containerd or Cryo are talking to a Kata shim that itself talks to a VMM, typically QEMU or Cloud Advisor or Firecracker. I don't have space to put all the VMM that we want to support. And this talks to KVM, which underneath talks to VT in the Intel implementation or some other hardware virtualization technologies. And that basically builds a virtual machine where the whole Kata stack, the Kata kernel, or whatever kernel you want to use in the guest, plus the Kata agent will be brought up and start the container workload or the pod workload inside the virtual machine. In the confidential computing proposal that we're putting together, that changes quite a bit. And basically the Kata would have to again use the new VMM APIs, the additional APIs for enabling the data protection that those hardware technologies provide. For QEMU, for example, this is it's called guest protection, I think. Cloud Advisor has another set of APIs for enabling this. But it is fairly transparent. It is probably the simplest aspect of enabling confidential computing with Kata containers. Just a set of simple APIs to enable. And KVM is doing a pretty good job at abstracting all those hardware subtleties away from the VMM and providing a fairly simple API. But on the guests, we would have to run the image service itself. And again, the image service would be responsible for downloading and decrypting the image layers from inside the virtual machine. And decrypting would happen after the attestation process that would allow for provisioning the guests with the right keys. And again, this is where we're currently we're currently talking about all this and discussing about all of this. Quite a lot of input from different folks that are interested in that approach. Feel free to chime in and add more to the discussion. I think I came up with that proposal. I'm an Intel employee, and my proposal I think is quite biased towards supporting TDX, which is the Intel implementation. Not because I'm trying to push just TDX, but because my expertise and my knowledge is better on TDX than on other hardware technologies. So if you have more insight and if you have more expertise and input that you can bring into that discussion, please join and help us. And I'm ready to take more questions if there are some more.
Yeah, there was one that came in. Do you think that OCI artifact types will help this in any way?
I'm not sure what we mean by OCI. Oh, OCI artifact type will help in any ways. I'm not sure. What I think is gonna the OCI dependency that we depend on is the currently container image layer encryption proposal that's being discussed in the OCI image specification. So I'm not sure about the artifacts there.
Why not allow Containerd and Cryo to download encrypted image layers on the host, but then decrypt those layers in the guest instead of a new image service?
That could be another architecture. We can that would be another option, but I think we would need Containerd and Cryo to basically, it would be a split architecture where Containerd and Cryo would just download the image, but not mount it. And there would still be a need for, since the image is going to be decrypted inside the guest, you don't want Containerd and Cryo to decrypt inside the guest. Yeah, we can reuse images that way, but we can also reuse images in the way that we're proposing, because the images would be decrypted inside the guest, encrypted when being stored, whatever in whatever storage the host is using. And I think at the end it doesn't really matter. But what really matters is I think the proposal of having a Cryo and Containerd downloading only the image and then letting the rest be handled by the guests would basically make things more complex, because it would be kind of a split container image services between the host and the guest. I think I believe it's simpler to just take the container image service and move it completely inside the guest.
More question. Do we need to trust the Kata agent inside the VM for this to work? And if so, is the Kata agent something deployed by the infrastructure owner?
Yes, we need to. In that architecture, in that proposal, the Kata agent is part of the everything inside the guest is part of the trust of the guest TCP. So the Kata agent, as I said, is something that should be measured, and the tenant should be able to attest the whole stack up to the Kata agent. So before provisioning and giving the Kata agent the keys, you obviously want the tenant to attest that the Kata agent is the one that is supposed to be running there.
And I think that's it for questions, and good timing, because that's it for the session. Thank you so much. This was a great session. Yep, Eric said sweet talk, and I agree. Thank you so much. Yep,
Thanks,
enjoy
everyone.
the rest of the conference, everyone.
Bye.